Okay, folks, we should be pretty well done with the quiz at this point and timed out. So let's go ahead and pick up with where we need to pick up. So what we're going to talk about today is essentially an overview and a bit of an extension of the video that you watched last night, which focused on precipitation reactions and solutions. So we're dealing with reactions that occur now in aqueous solution, and we talked about the various types of them in the video. So we have precipitation reactions, we can have acid-base or neutralization reactions, and then finally we'll deal with redox reactions. So let's focus today on precipitation reactions. Now, I think before I actually want to do this, I have a little example here that I'm showing on my whiteboard that we're going to come back around to. But another thing I want to just introduce to you before we get any further with this, I probably should have just shown it up there immediately, are the solubility rules. So they're posted up at D2L. I also sent them out in an email for you if that's more convenient to you, if you want to print out a hard copy or something like that. And also, these are the same solubility rules that you'll be using in the lab. So they're a very comprehensive set of rules that help us to determine whether something is going to be soluble or insoluble in solution. All right, so, and it's going to be the very same set you'll see in the lab, so you don't have to deal with learning different sets. And by the way, you can use these solubility rules anytime you need to. You don't have to memorize these or anything like that. So that's why it's sometimes nice to have them printed out so you can just grab them when you need them. I've got them here, so let me just pop out of this real quick. Go over to my files so I can show them to you. Okay, so there they are. All right, so basically the way this chart's going to work is it tells you that the salts of these ions are soluble. So basically what this table is doing is telling you what is soluble. Any of the exceptions that you see in here are telling you that something is insoluble. All right. So another thing to keep in mind here when you use this table is that it's hierarchical. So essentially we start with 1, and if that satisfies our ability to define whether something's soluble or insoluble, item number doesn't apply, we go to item apply. If that doesn't apply, we go to 3. If that doesn't apply, we go to 4. If that doesn't apply, we go to 5. Okay. And if none of those work, then the assumption is that the species is insoluble. Okay. So that's how the table is going to work. So it's kind of nice to kind of keep it handy next to you if you have it, on a different device or maybe as a printout or something like that. So as we work through our example today, or when we're doing our practice problems in Chem 101, you can refer back to this to make those judgments. Okay, so I'm going to pop back out of this and back over to my notes.
A quick question.
Yeah, go ahead.
For the quiz we just took, we have to put the charge on the reactants now?
Yeah, if there are ions in there, you got to put a charge on the ion. That's the important thing. And I'll show you that actually as we go through the example here. Charges become very important. All right, so I've got this set up so that we've got 2 species that are soluble in solution, and they're going to combine to give us something that may be soluble or may be insoluble. And that's what we need to sort of look at here. So the very first thing we would do here is we would come up with a balanced chemical reaction equation, and that's what we call the molecular equation. Okay, so I give you the 2 reactants. So we have to get from names back to formulas. And this is just good practice because sometimes Chem 101 puts the problems in these terms. So copper 2 sulfate, all right, so that's copper. Sulfate's polyatomic, right? That's SO4. Now, I want to make sure that the charge balancing is correct here. So copper 2 tells me that copper has a 2+ charge on this thing. Sulfate always has a 2- charge. Now, if you see it as and this goes back to your question you just asked, if you see this as a molecular form like this, you don't have to put the charges up there. Okay, I'm putting them up there just so we can verify them. All right. Now, the other thing that we're going to have here is going to be sodium carbonate. So that's going to be sodium, that's Na. Carbonate's also a polyatomic, that's CO3. Okay, now we got to get the formula right by charge balancing the thing. So carbonate always has a 2- charge. Sodium always has a 1+ charge. So now the question is, to get charge balance across this compound, I need 2 sodium ions to do that. So I put the 2 downstairs there. Okay. So basically we're making sure we have the right formulas before we do anything else. Now, while we're here, let's check our solubility rules and see whether these things are soluble or insoluble. I already told you they're soluble, but let's verify it. All right, so we got copper 2 sulfate. So does anything in item number 1 apply? No, it doesn't. All right, so I go down to item 2. No, I don't see anything about copper 2 or sulfates in there. Oh, but when we get to item 3 in the solubility rules, there's sulfate. And it tells me that salts of sulfates are soluble unless they are one of these other ions, such as lead 2, lead 4, strontium 2, calcium 2, barium 2+, mercury 1, or mercury 2. Now, does copper 2 show up there as any of those exceptions? No, it doesn't. So that tells me that that salt of sulfate is going to be soluble. So I put a little AQ down there. And by the way, that is important. Remember, that's a state of matter. So Chem 101 is looking for that if you have to write a reaction. So let's go back over to your sodium carbonate now. All right. Item 1 in the solubility guidelines takes care of that right away, because remember, it's hierarchical here. Sodium is a group 1A ion, right? It's in that first column. So all group 1A ions are going to be soluble. All right. So I know right away, without having to go any further, that this guy gets an AQ under it. Okay, so now, how do we get to the products of the reaction? What do we have to do? Well, if we watched the video last night, we know we let the ions exchange partners, right? So the cations exchange partners with their anions. So now the copper is still copper 2+, just to remind myself of that. But now it takes carbonate, right, as its partner, CuCO3. That's also a 2-, so I know I got the formula of that, right? And what does the sodium take? Well, the sodium has to take the sulfate. So I'm going to write NaSO4. Okay, but remember, sodium's always 1+, sulfate's always 2-. Oh, I need 2 sodium ions to balance out the charge on the sulfate. So I can put the 2 downstairs there to show that. So now let's go back to our solubility rules and check things here. So I got to put AQs or S's or whatever after these things, after the arrow here. So let's look at the copper 2 carbonate first. So item number 1 doesn't apply. Okay, do I see anything about coppers and carbonates in item 2? No, I don't. How about in item 3? No, that's about sulfates. Okay, item number 4 is chlorides, bromides, iodides. Do I see any of those? No, I don't. Item number 5 is calcium ions, strontium ions, barium ions, hydroxides, and oxides. So none of these things in the table actually apply to copper 2 carbonate. Okay, so remember, if nothing applies, that tells me that the thing is insoluble. So I'm going to put an S down there to show that. Now, how about my sodium sulfate? Okay, well, hierarchical. Sodium is a group 1A. We're done. So I can put an AQ after that. Okay, now I'm not done yet, guys, because I haven't balanced the reaction equation yet. Sorry, I bumped out of that. I haven't balanced the reaction equation yet. So we've got all the formulas right. We've got the states right. But now I got to make sure the equation balances. So I'm going to check that. 1 carbon on the left, 1 carbon on the right. We're good. 1 sulfate on the left, 1 sulfate on the right. Looks like we're good. 2 sodiums on the left, 2 sodiums on the right. We're good. Carbonate on the left, carbonate on the right. I think we're balanced. Everybody agree with that? All right. So at this point, I have got a balanced molecular equation. Now, normally this is what, if somebody like Chem 101 or anybody asks, write the balanced reaction equation for this reaction. Generally, they're asking for the molecular equation unless they state that they're asking for something else. So this is what you would write. But we know we can go further with it. Because again, if we go back to what we did in the video, I can take a molecular equation and I can convert it into what's called an ionic equation. Now, this is the important part here, Because remember, in an ionic equation, what we're showing is that any soluble species can dissociate. Okay, so soluble means dissociates 100% in solution, as we said in the video. Now, here's how we would do this. Anything that has an AQ under it in our balanced reaction equation, we're going to dissociate. Okay, so here's what we're going to say. For the copper 2 sulfate, we're going to get copper 2 ion. So I'm going to put that 2 plus up there, and I'm going to put an AQ after it. Now, this is where the charges really matter, guys. When you take a salt and dissociate it into its ions in solution, now they're ions. They have a charge. Okay, so that charge has to show up in the equation. Okay, so this is where charge becomes important. I'm going to do the same with the sulfate. See how the copper 2 sulfate breaks up into its component ions to give you copper 2 ion and also sulfate ion. You can do the same thing with the other reactant. Now be careful here. When this dissociates, this sodium carbonate, you're going to get 3 total ions per dissociation. Because when it comes apart, you're going to get 2 sodium ions and 1 carbonate. And the way you got to show that is like this. You put the 2 out front to show that you're getting 2 individual sodium ions from the dissociation. Okay, now you'll see students try to do this sometimes. Okay, that's something different. That's something different. That's insinuating that the 2 sodium ions are staying together as a unit, which they don't. Okay, so you want to make sure you don't do that. All right, so again, I'm kind of showing you basic mistakes people make as they go. Carbonate comes out, that's your CO3, keep a charge on it, and that's aqueous. So notice that all these ions have charges on them. Okay, so this is the important part. When you show a dissociation, you've got to put those charges on those ions. Now, what do I do with the copper 2 carbonate that has the S under it? Do I dissociate that into ions in this case? Anybody have an idea on that?
Oh, sorry, can you say it again?
Could I ask that again? Yeah, look at the copper 2 carbonate on this thing. I'm going to draw an arrow down to it. That thing, that whole compound there, that whole molecule. Am I going to break that up or leave it as it is?
Leave it.
Leave it. Yeah, you got it, because it's got the S under it. That's telling me that when this reaction happens, this is going to be a precipitate that we form on the bottom of the container, right? So that means it's not going to break apart into its component ions. So I'm going to go ahead and write that as CuCO3. And again, I don't have to put charges over this, because in this case, all I did up top there was just verify that the charges are what they are, so I can verify the formula. I don't have to write them. Okay, so I've got copper 2 carbonate. And then, oh, this looks like this thing's aqueous, this sodium sulfate. But again, I'm going to get 2 sodium ions. And since it dissociates, make sure you put the charge on it. And you're going to end up with 1 sulfate. Okay. So now I've got a balanced ionic equation here. So this is showing how anything that can dissociate into ions, because it has that AQ under it, will dissociate into ions. Okay. So then there's one other way I can write this. And it's that so-called net ionic equation. I think we did one of these in the video as well. And what we do in the case of the net ionic equation is I look for anything in the ionic equation that looks exactly the same on both sides of the arrow. And if it does, we're going to call those things spectator ions. Now, why do we call them that? Well, we call them that because they're not taking part in any way, shape, or form in the formation of the solid precipitate. An example of that would be the sodium ions. Notice that I've got 2 sodium ions existing as aqueous sodium ions on both sides of the arrow. So because they appear that way on both sides, I can cancel them out. So I'll just put a line through them to show that I can get rid of them. What's the other obvious spectator ion that you see there?
Sulfate.
Sulfate, very good. So we can get rid of the sulfates. Okay, and now if you look at this, the only things that are left here are the two things that come together to form our precipitate. Okay, so now that's what I write down for my net ionic equation. So I've got copper 2 plus, and again, put an AQ back there to show that this is actually what we have, plus carbonate, CO3 2 minus, and again, I get an AQ under there, because Chem 101 cares about these things. And then we're going to go all the way over to the other side. Those two ions are going to come together to show, or rather to form our CuCO3, and that is a solid. Make sure you put that S down there. Okay, so again, things that are important. State stoichiometric coefficients. In this case, it's just 1 to 1 to 1 to 1, so you wouldn't need to put them in, but if one of them had a 2 or a 3 in front of it, that has to be there. And then the other thing for our ions that are important are the charges. The charges have to show up there. Okay, so that takes us back around to the original question that got asked. All right, any questions about this one, guys? And this is basically taking us through the very same thing that the example from last night's video did, but now we were actually able to come in with some solubility rules and make some predictions about what our insoluble species is. Now, we won't always have an insoluble species. That's why we need to make sure we go back and use those solubility guidelines appropriately, because sometimes you'll write one of these reactions and you'll let the ions exchange partners and you won't find a soluble species. There won't be a product. So in that case, there won't be a precipitate. All you've got is a beaker or a container full of ions running around. Okay, so there wouldn't be a reaction in that case. So you're looking for that formation of an insoluble species. All right.
Will the
Questions
insoluble product always be solid?
It depends on the kind of reaction. If we're talking about a precipitation reaction, like this type of reaction, again, it goes back to the classifications of reactions that we're going to eventually talk about. In this case, if we're dealing with a precipitation reaction, it is a precipitation reaction because we're forming one or more solid products on the right-hand side. Okay, that's the definition of it. So that's why we're talking about that kind of reaction here. But can you have reactions where things come together and don't form solids? Yeah, sure. In other words, those are situations where things don't come together at all. Or sometimes, like in the case of an acid-base reaction, we end up forming water as a product. So you got a liquid instead of a solid. All kinds of things like that. But in this case, we're focusing in on our precipitation reactions. And the definition of that kind of reaction is that you do form a solid.
Okay.
Make sense? Any other questions, guys?
Can you please explain how you got the net ionic equation? Because you kind of cut out when you were talking about it.
Sure, I'd be glad to. Yep, so take a look at your ionic equation. Focus back on that. Okay, so if you look at that, what you're looking at is you're trying to get rid of any kind of ion that looks the same on both sides of the reaction equation. So notice the things that I crossed out there. Do you see the sulfate there and how I crossed it out on both sides?
Yeah.
Yeah, that's what we call a spectator ion, because it's not actually taking part in the formation of the product. That's the solid. Notice how I did the same thing with the sodium ion because it appears the same on both sides of the arrow. So I got rid of it in both places. So it's kind of like, you know, like in an algebra equation, if like a 2 shows up on both sides of the equal sign, you can cancel it out. It's the same idea. Kind of those basic rules of algebra. Now, why do I not cancel out the copper 2 plus? Oh, because it's over here partaking in the formation of the solid copper 2 carbonate. Okay, so if it gets used up and in the solid, then I can't scratch it out. And you can verify that by saying, well, it doesn't look the same on both sides of the arrow, right? It's a copper 2 ion by itself on the left, but there it is as a copper 2 taken up with the carbonate on the right-hand side to form a solid compound. See how they're different?
Yes.
Okay, perfect. Now, glad you asked the question there.
Thank you.
No problem. Any others, guys?
I also had a question.
Please ask.
So from the molecular equation to the ionic equation, how do we know that it disassociates?
How do you know? Okay, so that's where your solubility rules come into play. So see how everything that has an AQ under it, I let dissociate into ions.
Yeah.
See there with the copper 2 sulfate, it's got an AQ there, so that tells me I can break it down into its component ions. And I know that because copper 2 sulfate is a soluble species. Okay.
Okay.
So in a case like this, you have to predict. I didn't tell you, for example, up here in the original problem, I didn't tell you that it was soluble, right? So you had to figure that out. So how did we figure that out? We applied the solubility rules to it. That's how I know whether to put an AQ down there or an S down there. Does that make sense?
Yeah.
Good. So that's like one of the very first things. Once you actually develop your formulas in the molecular equation, once you know what they are, the next thing you do is you have to figure out that state. Is it going to be an AQ or is it going to be an S? And that's where the solubility guidelines help you out. We're going to practice with that in Chem 101 here in just a minute. So you'll get to see that in a little bit more detail and certainly ask questions there as well. Any others, guys, before we hop over to Chem 101 for a little bit? All right, let's practice. And again, ask questions as we go with this. So let's see, we want in class, chapter 4, and we want precipitation reactions. We are going to start that little operation here. There we go. And there they are. So these first few problems are really just kind of dealing with your solubility guidelines. In other words, is something going to dissociate or not dissociate in solution? And actually the first one with the CH3OH is a good one to just sort of talk a little bit about. And that one is a situation where we have a molecular compound, right? So notice there aren't any ions in that, right? Those are all nonmetals combined to other nonmetals, right? Carbons, hydrogens, and oxygens. So we know that that's a different kind of bonding. That's covalent bonding. So we don't have any salts there. So a good rule of thumb is that molecular things don't dissociate. Now, that's not always true, but in this case, you know, we can kind of take that one to the bank. So if you see something molecular like that, you can pretty well assume, okay, it's probably not going to come apart into ions. So you're looking primarily for salts, right? Metal and a non-metal.
I had a quick question, Dr. Damon. So when talking about this topic, are you saying that men in society look at women as no longer successfully do that, we weren't able to become a mother. Okay. Yes, it makes sense. Thank you.
Any questions so far, guys? Anything there you want to see?
Number 6, please.
Number 6? Yeah, we could do that one. K2SO4 FeCl3. Hang on. What was the other one? K2SO4 and FeCl3, was that it? I think those were the two ions. Am I right about that for number 6?
Yes.
Okay, thanks. Okay. So the very first thing we do is just check solubilities all the way around, right? So, first one, potassium sulfate. I know that's got an AQ under it because it's got a potassium there. Potassium's a group 1A. Know that one right away. FeCl3. Okay. So that's a chloride, right? So that's item number 4. Now, it says chlorides are soluble except for silver, lead, mercury. Does it say anything about iron there? Well, it doesn't. So I'm going to assume that that's an AQ, right? Because chlorides tend to be soluble. Now we got to let the ions exchange partners, right? So one thing I'm going to make is potassium chloride, which is KCl. That's a 1 plus and a 1 minus. So I know I got the formula right. It's an AQ because potassium is a group 1A. That's rule number 1. And then what about the other one that I make? It looks like it's going to be iron 2, or let's see it, iron 3 sulfate maybe. FeSO4. The iron looks like it's iron 3. I know that because the chloride is a 1 minus and I have 3 of them. So that means the iron has to be a 3 plus. That's Fe3 plus. Sulfate's always that, 2 minus. Oh, so to get those to match up, it looks like I'm going to need 3 sulfates and 2 irons. Everybody see that? 2 times 3 is a 6 plus, and 2 times 3 is a 6 minus, which cancel out. Okay, so part of it's making sure you get the right formula there. Now the question becomes, is that soluble or insoluble? Do I put an S or an AQ under it? I think that's what the question was asking, right? So we go back to sulfates here because it looks like this is one that deals with a sulfate. And it says that sulfates are soluble, right? Except for lead 2, lead 4, strontium, calcium, barium, mercury 1, and mercury 2. Okay, so does the iron show up there at all? Sort of the same rule we applied to the FeCl3. You see an exception there for iron 3? I don't. So what this is telling me that this should be a soluble sulfate. So I've got an AQ there. Okay, because it doesn't show up as one of the exceptions. So do I have a reaction here? Everything's got an AQ under it, right? So do I have a reaction? There's no solid, so I don't have any reaction. So this one would be NR or no reaction. Hopefully we got that right. We'll go back and check. I'll leave that up so anybody who wants to copy it down or look at it can. Oh, did I by the way, just for the sake of completion, we should probably balance the reaction equation. We really didn't have to do it in this case to predict what the thing was, but let's just do it. I got 2 potassiums on the left. I need 2 on the right, so I put a big 2 over there. Okay. And let's see, looks like my chlorines are off. Was that an FeCl3 or an FeCl2? That just seems weird that those would turn out that way. Well, no, that's going to work out right. So 2 irons, so I need 2 irons. That's going to give me 6 chlorides. So actually that needs to be a 6 there, doesn't it? And then I've got what, 3 sulfates. So I'm going to need 3 of these guys over there. So that's going to give me twice 3, which is 6 potassiums. Yeah, that works. 2 times 3 is 6 chlorides. That works. 2 irons and 3 sulfates. Yep, it works. So yeah, we'll just put a big NR there for no reaction. See if we got it right. Yep, we got it right. Oh, it actually does say complete the balanced reaction equation, doesn't it? Okay. Well, we didn't have to in this case because we got an NR. So everybody see choice 2 down there? That's pretty much what I wrote, but why would that have been considered wrong? Why did they, why was that marked wrong there? Again, this is getting into the weeds with Chem 101. Well, it's because you're supposed to write NR after it, and that didn't happen. So technically, that second one is correct, but you got to follow Chem 101's instructions. All right, guys, we're down to about a minute or 2 of class, and also for the assignment. Just let me summarize a couple things for you guys to think about for next time. If you're struggling with this, guys, practice it. I mean, there's plenty of practice problems over in the homework. So make sure you're up with this. Make sure you're comfortable using those solubility guidelines. That's another thing you want to make sure you're able to do, and do fairly quickly. So again, that comes with practice. As far as next time, we're going to jump into some acid-base reactions, which is the next class of reactions that we want to talk about in aqueous solutions. So that's the next video. So then, of course, be ready for a little 5 for 5 on Wednesday. Anybody have any last questions? Thought I saw somebody starting to pipe up there.
Is hydrogen, sorry, Is iron hydroxide soluble?
Iron
Because-
hydroxide, would that be like iron 3 hydroxide? I think that's what it showed up as.
Yes.
Okay, so let's take a look. Where does it talk about? There's no place specifically where it talks about iron here. So you have to come down to category 5 in the solubility rules. And it says that calcium, strontium, and barium hydroxides are soluble. Okay. But does iron show up there? It doesn't, right? So what are you going to, what is that going to tell you about iron 3 hydroxide? Soluble or insoluble?
Insoluble?
You got it. Yep, that's how you do it. All right, so I think I'm about done here, guys. So you guys have a good rest of the day, and we will see you on Wednesday. And practice, 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 folks.